All right, so about the length of the exam. The length of exam is 1 hour 20 minutes, right? And 20 to 25 multiple choice problem. Okay. All right. So in the last lecture, we talking about the mass conservation and momentum equation, right? The Newton's second law, when we have in the a control volume, and so for the mass conservation, right? Since there's no, for the system is very simple, right? There's no mass changes in the system, and after we apply that derivative correlations for the control volume related to the control volume, so basically we obtain this equation as the mass conservation for control volume. So you can see that okay, so basically the mass conservation equation will contain two terms, right? The first term, so this one, this is the change of the mass regarding to inside this control volume, and the second term is the mass flux across the control surface. Okay, and similarly, we are even when we're using the Newton's second law, we also try to derive the that momentum equation, which is working for control volume, and in these cases, okay, the force will also equal to two terms. The first term is the change of this linear momentum inside this control volume, and the second one is actually this momentum flux. Okay, the net momentum flux, leaving this control volume through the control surface. Okay, and due to the force. And one thing I forgot to mention during the last lecture is that based on if you can recall what you learned from your dynamics class, right? This Newton's second law is not working, in all cases. Okay, there is a requirement for the Newton's second law that F equal to ma, and that requirement is that this Newton's second law is only working for the initial frame. Okay, so what is the initial frame? Initial frame is either this frame is static, or this frame is moving with a constant velocity. Then, in other words, so which means that this coordinate system itself won't have any acceleration in respect to absolutely still, okay, no velocity frame. Okay, so since that this momentum equation we developed here is based on the Newton's second law, so we have the same requirement here. Okay, so which means that this equation we derived here, the last class, is only working for the initial frame. Okay, and so if it's not the initial frame, so this equation form will not be same. Okay, which we were talking about in the future class. Okay, we will go there later. And also at the end of the last lecture, we try to go through an example problem on how we can use this momentum equation in this control volume to solve some fluid problems. Okay, and we didn't finish that problem. Okay, this is an example problem where we left during the last class, and in the last class we were seeing that for this problem you may have multiple ways to determine, to define the control volume, right? So in these two pictures here, the first picture is the first way we define the control volume, where that the control volume we including the fluids at the place, okay, both fluid and place. And you also have the second way. Okay, the second way is that when you define the control volume only contains the fluids. Okay, so this plate part is not including inside this control volume. And regarding to the first method, this control volume method, we just apply that we can just apply this momentum equation directly to this control volume, because that is for this problem is asking for us that what's the force this hand need to given, okay, to hold this plate. Okay, and since this hand, since the plate is including inside this control volume, so this force is also basically you can consider this the force through this hand is applying on this control surface. Okay, and you know, when we applying this x direction force, so we finally get that you know get that what the force this hand need to hold is, you know, by using this momentum equation, by applying this momentum equation. Okay, this is the first way to do it. So let's continue from where we stopped in the last lecture. Okay, and think about the second way. So when we just define the control volume, you know, into this kind of control volume, only including the liquid. Okay, only including the fluid. So there is the plate itself is not including inside this control volume. So in these cases, okay, when you apply this momentum equation, right, and when you try to find the force, all those force, because that, you know, in the momentum equation we have the force for as the surface force or body force, right? And the body force is the weight of this fluid itself, okay? And when you consider the surface force as the interface between this control volume and the plate, you will also have a reaction force, you know, working, you know, by this plate on this fluid, okay? And we can still using the momentum equation, okay? And after we using that momentum equation, you know, we can guide this reaction force between the plate and surface, because this is the force where we change the moment, the x direction momentum. Okay, we change the direction of this flow velocity from the x to the y. Okay, because that at the inlet at the location 1, right? You know, all the velocity is in the x direction. After it hits the hit this plate, right? All the velocity is changing to this positive minus negative y direction, and which means that you know, the momentum is changed, and it's changed due to this force. Okay, this reaction force between the plate and the fluid, and we can simply apply the same, okay, x direction momentum. Okay, and this f of sx will including the you know, the atmospheric pressure here, and but this atmospheric pressure will be also, you can think that, you know, on the back of the plate. So because that on the fluid, okay, at the interface, okay, and on the interface between the fluid and the plate, right? So there's no is not exposed to the atmospheric pressure, right? So you need to consider that this atmospheric pressure due to, you know, due to the environment. All right. So you will have this when you consider the x direction force for this kind of control volume, you need to consider this atmospheric pressure here times this AP is the area of the plate. You get this x direction, you know, pressure force due to atmosphere, and this B is the body force, okay? And let's assume that you know, this Bx force is something, and it's not body force, okay? It's considered as a reaction force, okay? I don't know that why they are using the different notation here, okay? So this Bx is consider this Bx force is the reaction force between the plate and the fluid, and you know, we're using the plus sign here because, like, let's assume that this Bx force is on the positive x direction, or know that they are indeed the negative x direction. But it doesn't matter, because that when you solve this, you will get a negative value, okay? Which means that the direction of this force Bx will be to the negative x direction. And this force, x direction force, will equal to the change of the x direction momentum of the fluid, right? And for the x direction of the momentum of the fluid, we know that at this inlet 1, we have this x direction velocity, and then when it hits the plate, you know, there is no x direction velocity. So the change of this force is simply equal to this u here, at this inlet velocity, and times rho density, and times this area, this nozzle area, okay, at the inlet. Okay, so you have rho u and area, and this v dot a, okay, this area is this nozzle area, the normal direction is going to right, positive x direction, and this v is just equal to u. All right, and this V is just equal to so this V should be just equal to the U, and the reason you have this negative sign here because that you know you need to using if you don't if you denote that the location 2 as a fluid under this plate surface, right? So you should using the momentum as this position 2 minus position 1. But at the position 2, since that velocity is 0, so which means that at the position 2 on this plate there is no momentum. Okay, so you're using 0 minus 1. That's the reason you have this minus sign here. Okay, so you have minus, the result you get is minus u1 times this you know u1 again, and times this a direction, a area at this nozzle, and the result you get is this minus 2.25 kilonewton. And remember that this result you get here, okay, is equal to this force, which including both the pressure force and this reaction force here. And you can find that this reaction force will be equal to you know, just subtract this pressure force from the both side. You get this value, and you can see that this value will be a negative value. So which means that this reaction force will going to left, go to left. Okay, negative x direction. But if we go back to the original question, right? Original problem. So that what we want to get is that the force required for this for our hand to holding this plate, right? And then because that right now we only get this reaction force, right? Between so this bx is the force, this plate, you know, acting on the fluid. Okay, and then if we want to get that the force required by the hand, so we need to study this plate itself. Okay, so this problem becomes a static problem. All right, not fluid problem. So the second step is that we need to study this static problem. So we need to draw this free body diagram for this plate. Okay, and for this plate, we are going to have their reaction force between the fluid and plate, and which we already solved it. And also that on the right-hand side, we will have both the hand, the force from the hand, and also the pressure force at the back of the plate. Okay, so you draw this free body diagram and using what you learned from your static class. And on the x direction, you know, the summation of the force should be equal to 0 because that this plate is still. And you can immediately get what this, you know, the force required by the hand. Okay, and you have this negative sign for this bx because that this bx we solve is between the force for the plate acting on the fluid. And when you study the force on the plate, it will be the force for this force from the fluid apply on the plate, right? So which is a reaction of this bx here. So you need to add a negative sign here, okay? And so you on the back on the back side, we also have this pressure force. This one value will be cancelled with the pressure force. This term you have in this bx will cancel out, and so it will telling you out. Okay, this will be the force required for your hand. It will be same as this value here, and you also see that it's a negative value, and it's showing that you know it will require that this force to be the negative x direction. Okay, and so from this problem you can see that you know actually when you study this when you want to try to apply this mass conservation or this momentum equation, right, for fluid problem, you have different way you can define the control volumes. Okay, and so which way should we use, right? So it's determined on the problem. It determines that what value you want to seek. Okay, and for this problem, okay, if you only want to find, okay, what's the reaction force between the plate and fluid, if you only want to find what's the reaction force between the fluid and plate, I think this method is better. The second way is better, because that you know the control volume will including only the fluid, and the force we want to find will directly working apply on the surface, this control surface. Okay, so this will simplify the problem. And for this example problem, you know, instead of we want to find the reaction force between the fluid and plate, actually we want to find the force, you know, by this holding, you know, the required to hold this plate by hand. Okay, So in these cases, since because that the force we are looking for is this hand, the force from the hand, I think this the method 1 is better, because that in these cases this force we are looking for is directly apply on this on this control surface. And if we are using the second one, we make the problem 2 steps, right? As you can see that the first step is that we need to find this reaction force first, and then after finding the reaction force between the fluid and plate, we need to do a static analysis for this plate and to find this what's the force required by the hand. Okay, so this makes you may need an additional procedure to do that. Okay, so this example problem just show you that you have freedom to choose different, using different way to choose to define the control volume. Okay, but some method will give you, can simplify, some definition. Okay, of some way to define your control volume can simplify your work to solve the problem. All right. And do you have any question here? I see somebody is chatting. Any question? No? Okay, so let's go through one more example problem, right? So there we can apply the this momentum equation. Okay, please read this problem. Okay, so for this problem, we have a container, okay, and this container has the weight itself, has its own weight, and there will be the water inside this container. There is an inlet port on the top, and also has 2 outlet ports at the bottom. Okay, this location 1 will be the inlet, and location 2 and 3 will be the outlet. On the top, okay, there will be more water is adding into this container, and also the depth of the water inside this container is known as h. Okay, and the question is that if we put this container on a scale, okay, what the weight value will be reading by this scale. Okay, in another word is that what is the reaction force between this weight and this container. And so the first question you were thinking that you ask yourself that if this weight value reading from this scale will be just equal to the weight of this container plus the weight of the water, and the answer is that is no, right? Because that the value you are going to read from this scale will be the value which will be larger than the sum of the weight of this container and also the weight of this water inside. Why? Because that on the top you have more water is adding, right? And this water you adding from the top will give you some additional y direction momentum, right? Because you have this inlet there on the top, and on the negative y direction you add some momentum there to the system. And then if you're looking at the exit, the location at this part 2 and part 3, you see that all the velocity is changing to the x direction, right? So which means that in this cases you have a momentum change on the y direction, because that on the top you have y direction value, but when you go to the bottom, there's no y direction velocity anymore. Okay, and so you have a y direction momentum change, which will require you that you need to provide additional y direction reaction force additional reaction force between this container and the weight, right? Between the container and the scale, so that it can make this change of the momentum happen. Okay, so our without calculation we are going to know that okay, for this problem the value you're reading from this scale, that number will be larger than just the weight and the water, the weight of the water and the container will be a little bit larger than that. Okay, because that we need an additional force that to change this inlet flow on this y direction velocity, this momentum to change it to from this inlet value v value to the 0. Okay, so to calculate this, what's exactly this reaction force between this container and scale, we need to first define the control volume. And the way we define the control volume for this problem, because that the force we are searching is the force between the container and the scale, right? So we can directly define our container using this blue line here. So, but if we define our define our control volume in this blue line, and we will making that this Ry, this reaction force between this scale and this container, will be the force directly apply on this control surface. Okay, so by define the control volume in this way, so we can directly we can directly find what this Ry value will be if we apply this momentum equation for this control volume. All right, and so for this problem, and we have some assumption here is steady flow, so that the transient term is gone. So this is the momentum equation. This is mass conservation, and we also assume that incompressible flow. All right. Which means that the density is constant, and also at the inlet and outlet, let's assume that the velocity is uniform. Okay, uniform flow. And so the question is that when you want to find that what's the y direction force, right? So the y direction force, what the surface force on the y direction will be just equal to that reaction force between the scale and container, right? So this value is the value we want to find, and the body force on inside this control volume will including both the weight of the water and the weight of the container. So you have both the weight of water and weight of container, and the weight of the water is calculated by this how many water inside, right? This depth h here. Okay, and when we're talking about the surface force, right? You can see that we neglect the atmospheric surface force, atmospheric pressure force. Why? Because when you define this this control volume here, you can see that your pressure force, okay, basically you're applying on all the surface of this on all the surface of this blue lines, right? You have the pressure force here, you have the pressure force on the left, you have the pressure force on the right, and you have a pressure force on the bottom. So all the pressure force, since that they are going to all directions, so they are going to be cancelled out. Okay, so that's the reason that we didn't consider that one atmospheric pressure force there. And so this is the force, all the force we have here on the y direction. And what's the momentum change on the y direction, right? So it's similar to the problem we have previously, previous example problem. Like when you want to calculate the change of the y direction momentum, you need to using the momentum here, this at this point minus the momentum at this point. Okay, the momentum at the bottom minus the momentum at the top, and as the momentum y direction momentum at the bottom is 0, because there is no v velocity at the bottom. There is no y direction velocity at the bottom, and then so the change will be negative this v1 times a dot this v1 v value here, right? And this a dot this v value, and this error normal dot this v value will be a negative value since this is inlet. Okay, and so the result you get will be equal to this value. Okay, and v1 times minus rho v1 you have this minus sign here because that this is inlet part, right? So your v direction and your area normal direction is negative. Okay, and you got this value here, and remember that this v1 will be simply equal to the negative this v1 value. Why? Because that this v direct is this big V is negative in the negative y direction, right? Where is it? Because you have this v1, actually it will be negative y direction, so it will be negative of this yeah, minus negative 3 actually. And so you just substitute it inside, okay? So this is the momentum change, and you can directly put this everything into this momentum equation. You can directly calculate what the what the reaction force will be. Okay, you can finding out what the reaction force will be, and it will turn out that okay, so this is the value you are going to read from that scale. Okay, 614.8 Newton. All right, so for what's this problem telling us? So this is still similar problem than what we have right before, right? It's like we know that the change of the velocity, so that which means that we know that the change of the momentum, and we want to find that what the force we require to make this change happen, right? So it's a very straightforward one. And do you guys have any question for this example problem? No. Okay. So let's go through the last one. Okay, this will be the last one for this momentum conservation, momentum equation. Okay, read this problem first. All right, so for this problem, we have to flow inside a pipe, and this pipe is in this elbow shape, okay? And the special thing for this problem is that the inlet location part 1 and the outlet location part 2, their cross-sectional area is different, right? You see that for the inlet part 1, right here, you have larger cross-sectional area, and for the outlet part, this location 2, you will have a smaller cross-sectional area. So what does this mean? This means that if you are going to use the mass conservation, okay, which will telling you that the velocity at the part 1 at the inlet which should be smaller than the velocity magnitude at the location 2, right? Because that we want the mass conserved, and you have larger area, so you will have lower velocity. And so for this problem, okay, the special thing about this problem is that for this problem we are going to use both the mass conservation and the momentum equation. Okay, previous two example problem we only use the momentum equation. So this one we need to use both mass conservation and the momentum equation. Why? Because that in the problem description, it doesn't give us that what the velocity at the inlet, right? And it only give us the velocity at an outlet, and also it gives us the cross-sectional area of the inlet and outlet. So we need to go into use the mass conservation to calculate what the velocity at the inlet, what the velocity here. Okay, simply that rho times v1 times a1 should be equal to rho times v2 times a2, right? And so that we can get what v1 will be. And after we get the velocity at the inlet, and we are going to use the momentum equation to calculate the force, because that this is a 90-degree change on the flow direction. Okay, so you will have the force required on the both x and y direction, because that x direction will require you to x direction force is needed so that you can reduce the x direction momentum of this flow to 0. And the y direction force is required because that you are going to increase the y direction, velocity from 0 to v2. Okay, so that's why is that in this problem you need to solve this. You need to apply this momentum equation on both x and y direction. Okay, and the first thing is like of course we need to define the control volume. Okay, so for this problem, and the control volume is defined in this way here. And let's first consider the atmospheric pressure, the effect of the atmospheric pressure, right? So for this control volume we have here, okay, you can see that okay, this atmospheric pressure will, working on the both, top, bottom, left, and right. Okay, so in another word, so like we can, if we change, okay, this pressure from this inlet pressure P1 from the absolute pressure to the gauge pressure, so we can simplify the problem in this way. Okay, just assume that we have a gauge the pressure, on the inlet. So on all the other places will be 0. There is no gauge pressure. Okay, and so by this way we can neglect this, the effect of this 1 atmospheric pressure from the environment. Okay, so if we do that, okay, and we can just simply apply the momentum equation. Okay, the first thing definitely is that the first thing is that we are going to find the V1 value, and the V1 value is given by using this momentum conservation, mass conservation. So you can get what's the velocity at the inlet. Okay, so because we knowing that rho times V1 times A1 should be equal to rho times the V2 times the A2, and since we assume rho is constant, so you can divide the density on the both sides, and you can quickly get what the magnitude of the inlet velocity, V1, okay, will be equal to 4 meters per second. After we get this velocity at the inlet, so we can directly apply this momentum equation, okay, on both x and y direction. So let's consider the x direction momentum. So this will be the equation, okay, and this P1 gauge times A1 is the pressure force at the inlet, this surface force here, and this Rx value, okay, is the value required to. So assume that we have some clips to hold this this elbow, okay, to make sure that it's not moving around, and that Rx value is that clip, okay, that that force on the x direction to this pipe, okay, and so you have this Rx value will be equal to the change of this x direction momentum, right? And similar thing that we had before, because this is related to the inlet, right? So this V dot A will give you a negative value minus rho V1 times A1, and this V1 we already solved it. Okay, so this will give you the x direction force directly. Okay, and substituting what's this gauge pressure at the inlet, and what's the inlet area, and what's the inlet velocity. So you can immediately calculate what this Rx value will be. Okay, after you solve the x direction velocity, you can see that this Rx is a negative value. Why? Because that we assume this Rx direction is in the positive x direction, but we know that actually you need a force going left to hold this elbow, right? So that's why that Rx force is a negative value. Okay, that simply means that the force required to hold this elbow pipe in x direction should be in the negative x direction. And similarly, you can find the y direction force by applying this momentum equation on the y direction. Okay, and you have both you have this y direction force Ry here, and you also have the this you will also have this by value. What is by value it is? I think this by value is the weight of this elbow. Okay, this is pipe. because this pipe will also have some weight. Okay, so this is the body force on the y direction, so it will be equal to weight of this pipe, and also you have this y direction force need to hold this pipe. Okay, and will be equal to change of the, this linear momentum on the y direction. Okay, and on the y direction, you will have the, you do not have inlet part, you only have an outlet part, and the outlet part, the y direction, the normal velocity, the normal direction of surface area and the velocity direction should be same. So when you have this v dot dA, you get the same quantity. Okay, and then you have this v2. But remember that this v2 value, so this this big v is just the this big v is just the magnitude, okay, for this velocity. So this will give you a positive value here, and this small v should be the vector, okay, and you should consider that the direction of this v velocity because it's going down. So this small v2 should be negative big v2, okay. So this is the value, and substitute there. And if you neglect the, so this will be the result required for this y direction force. And if you neglect the weight of this elbow pipe, and the force you require should be this value, and is negative value because that you need force to holding up to against both the weight and this reaction force. Okay, so this is the last example problem we are going to go through for this momentum conservation equations. Any question here? No? Okay, so there is another two example problem on the textbook, and I will left it to the next week's recitation. Okay, the recitation after the exam. So I will let the TA go through it for you. And okay, and now let's continue to talking about this momentum conservation, momentum equation. Okay, and let's talking about some special cases for the momentum equation. All right, so we have that momentum equation we derived in that integral form, right? Basically, the force, the net force on the system, on this control volume, will including two parts, right? One part will be the change of the momentum inside the control volume, and the second one is that the momentum flux, the net momentum flux leaving from this control volume, okay, through the control surface. So that is the integral form. And let's try to derive a simplified, equation under some assumption, so that the equation we derived will not be in this complicated integral form. Will be a much easier form. Okay, and one example is this Bernoulli equation. So we will spending the rest of this class to go through the procedure how we can derive this Bernoulli equation. It's just a special case. Okay, it's special case for the momentum equation. And so what's the assumption we made here to simplify the momentum equation? The first thing we assume is the steady state flow. So there's no transient terms there in the momentum equation. That partial t term is gone. Okay, and the second one, no friction. So in another word, no friction means that no viscous force. Okay, so which means that we assume the problem has no viscous force. So what does it mean, no viscous force? It means either two things. Either the flow is inviscid, which means that mu equal to 0, or there is no velocity gradient. Because we know that tau equal to mu times du dy, right? Remember that this tau equal to mu of du dy we learned from the previous chapter. So when we have this tau equal to 0, which means no friction, no viscous force, you have two possibilities. Either your mu equal to 0, which means that the flow is totally inviscid, or this du dy equal to 0, which means that there is no velocity gradient inside the flow. Okay, so this is what the second assumption we make. Okay, basically it means that no friction, or you can see the no viscous force. Okay. And we also make an assumption like a incompressible flow, which means that rho equal to constant. And there is also a special assumption we made here. We assume the flow, the flow is along its streamline. So what does this mean? This means that there is no vorticity, okay? There are no rotation things, okay? And so which means that all the flow, okay, their direction they are going to moving, okay? If you track a particle, okay, inside this fluid, and this the motion of this particle with the time will be equal to this instantaneous streamline field, okay? And so by this assumption, all these four assumptions we made here, okay, so we can define a control volume. So in which way that we can apply this momentum equation. And let's assume that we have this control volume which we defined inside as shown in this picture. And because that we assume that all the flow is along with the streamline. So basically you can thinking that this control volume we defined here actually is being surrounded, okay, by being included with some streamline at the surface, right? So it's just like your tube, enclosed by this streamline, right? So all the surface of this control volume will be some streamline. So it's like we're using some streamline to enclose a region, enclose a tube there. And this is called the stream tube, okay? And let's assume that we have a surface area, at this location, okay? Let's assume that we define a coordinate, okay? Let's first define a coordinate, S coordinate, and this S is the displacement along this streamline, okay? And so let's assume here is S equal to 0, and here is the ds value, and so S coordinate is along this streamline here. Okay, at this S equal to 0 location, we are going to have all those quantities, okay? Let's assume some quantity here. We have the pressure, we have the density, we have the velocity, and we have the area for this control volume. And we assume that this velocity will be v equal v of s. This s means that this is the velocity is in this s direction, and that is correct because that we know that the flow is moving along with the streamline, right? So the velocity here has to be along with this streamline. So that's the reason we add s for the velocity. And if we define this, another end surface, okay, for this control volume at the location s equal to ds, so which means that along this s coordinate, and this distance is ds here. So we will have a new end surface here, and this surface will have their own value of the p, rho, velocity, and area, right? And it will not be equal to the value at the beginning surface, start surface. So let's assume that at the end surface here, we have the pressure at P equal to P plus dP. And density, since we can consider that it's incompressible flow, so density still be constant equal to rho. And velocity will become Vs plus dVs, which means that we assume small changes on the this s direction velocity. And the area, okay, this area can also not be as same as this area here. Why? Because that you have the velocity change, right? And this velocity times this area times density give you the mass flow rate. And due to the mass conservation, we know that the mass conservation here and should be equal to the mass conservation here. If you have smaller velocity, you need a larger area. If you have larger velocity, you need a small area, so that you can guarantee the mass is conserved. Okay, and so this is what we have here. And one special thing, the way we define this control volume, which this is so-called stream tube, is that since this control volume is defined by all these surrounding streamlines. Okay, so which means that at any location, at any point, okay, on this surface here, so local velocity direction will be along the streamline, right? So victory will be along this surface, surface direction here. So which means that you will not have any velocity on this normal direction to this S direction. Remember, this S direction is this blue line direction, right? So you won't have any velocity on the direction perpendicular to this blue line. Why? Because that this is how we define the streamline, right? Remember that how we define the streamline. Streamline is defined by assuming that at any location, any point, right, on this streamline, their tangent direction will be just equal to the, local velocity direction, which means that if you choose a point here, their velocity must be the tangent direction of this streamline. So which means that you won't have any velocity on the normal direction of this blue lines. So in another word, okay, on this, surface, okay, on this circular surface here, you won't have any velocity across this surface, which means that you won't have any flow, mass flow, and the momentum flow will go through this circular surface here. You only have those mass flow, mass flux, and the momentum flux at the end and at this start and this end surface. Okay. On this parameter direction, okay, on this circular direction, you won't have any, mass flux or momentum flux will go through or go into or leaving this control volume, because that we define this control volume, to make it align, align along with all these streamlines. Okay, so all the, either the mass flow or momentum flow is only kind of going in through this starting surface, or going out from this end surface here, cross-sectional area. Okay, so this is the special things about this one. And so after we have all this, after we define this control volume, and so let's consider first the continuity equation. And continuity equation just means that the mass conservation. Okay, it's just another name for the mass conservation, because that continuity means that you have to conserve the mass. Okay. And in this case, it's steady state, so there's no transient term. So you have this, which means that the net surface mass flux will be equal to 0. And in another word, the mass flux at this inlet will be the mass flux at this outlet. Okay. And at the inlet, this V dot A, because it will give a negative value, so you have this minus rho times Vs times A at the inlet will be equal to this value at the outlet. And outlet, this dot will give a positive value. So you have this rho Vs plus dVs plus A plus times A plus dA. Okay. So you write this out, and what do you get? You get this formula here. Okay. Vs times dA plus A times dVs plus dA times dVs plus dA times dVs equal to 0. And if you look in this three term, okay, and since we know that this dA, okay, and this dA value is a small changes, okay, so you can see that this is this term here is the multiplication of the two differential term. So which means that the order, okay, the quantity, the magnitude of this term will be much smaller than this two term, because that this is like you're using small term to time another small term, and this two term is like you're using a large time, macroscopic value times small differential value, and macroscopic value times another differential value. So you can neglect this value equal close to 0, okay, because as the dA, dV are both small values. Okay, even you times it, you become even smaller. Okay, so you can neglect this multiplication term between these two differential terms. Okay, so this is going to 0, and this is the only thing left here. All right, so this will be the for this control volume. Okay, when you have this control volume with all these 4 assumptions we made here, and what the mass conservation equation will be. Okay, velocity times area equal to times change of area will be equal to area times change of velocity. Okay, and so something like a notation here, because that control volume is bounded by the streamlines. So there are no y direction on this perpendicular direction, so you won't have any flux across the bounding surface, okay? And so which means that you have those mass flux and momentum flux, it only happens at this start and end surfaces, okay? Okay. So this is how we derive the mass conservation in this control volume. And now the next thing we want to apply the momentum equation for this control volume. Okay. And so this is the momentum equation we have here. And because we assume that it's steady state, so this transient term is gone. Okay. And so we have three terms left here: the surface force, the body force, and the the net momentum flux across the whole controlled surface, right? And so let's take a look at each term. Let's first looking at this surface term here, surface force. So what's the surface force that we have here for this control volume? And for this problem, the surface force is due to the pressure. Okay, because we only have the pressure here, we have no other force applied to this control volume at the surface. And so at the inlet, at this end, starting at this end, okay, we have this pressure force, normal to this to this surface, and its value will be equal to P times A, right? Because we know the pressure here, we know the area here, so this is the surface force on this location here, and at the end surface here, location here, we will also have another pressure force, right? And this pressure force is going to inward to this, going to left, right? Going to this inward direction for the pressure force. So you need to minus this P plus dP times this A plus dA, because this is the pressure at this location, and this is this area, this cross-sectional area at this location. Okay, but we will have an additional term. What is this term? This term will be the what is the pressure force applying on this bounding surface, right? And you may asking that why we have the pressure force on this bounding surface, and the answer is because that we have this area change, because that at this location we have the area A, and at this location we have area A plus dA, right? So in this situation, in this picture we draw here, we can see that the area, this cross-sectional area for this tube actually is increased at the end, right? So when you have the tube increase at the end, so you have the area here, and you increase at the end here. And if you want to consider this pressure force on this direction here, you will also have some pressure force on this bounding surface slope here, because that you increase the area, so you make some force can working on this bounding surface. So if the area is same, so you won't have any pressure force on this on this direction, because that you don't have an area which you can project on this location, on this direction, for this bounding surface. And for this one, it's possible, because that this if you do for this bounding surface area, if you do a projection on this direction, you will get this additional area, right? Like which can working on this pressure force here. And what this area will be? What this value will be? This value is just dA, because this is just the value. So if you draw it, so this is just the value like increase of this all this area if you do the projection for this surface area onto this normal direction. Okay, this area will be just equal to the dA, like which is the increase of this cross-sectional area. Okay, so that's the reason you have this dA here. And what is pressure force here? So let's make a arithmetic average, because we have the P here, we have the P plus dP here. So let's assume that this location, so pressure here is just the average of these two. Okay, we have just assume that this is or one half of this P plus this P plus dP, let's assume this pressure is just in the middle, it's just the average of this pressure of this at this surface and this surface. So that's the reason we got this pressure here. Okay, so by this way we calculate all the surface force on this S direction. Okay, you have the surface force on this starting phase. You have the surface force pressure force at the end of this phase, and also you have the surface force on this bonding surface. Okay, due to the increase of this cross-sectional area. All right, so this denoted as this D F of SB. Okay, the force will be like going to here, but and you have this area increasing, so that's the reason you have it. Okay. So you add all these three terms together, you can get that. Okay, so this will be our the whole surface force. So this is not correct. So this is equation 1. Okay. And so now we find the first term, and the second term is to find what the body force, right? And what is the body force on this S direction, right? And the body force will be just equal to the weight force of all the fluid, including inside this control volume, right? Let's assume that this G direction, okay, this is the gravity direction is in this negative Z direction, okay, and also let's assume that for this control volume, okay, we have this theta, theta angle between this Y and this Y direction. This is Y direction, right? Between this Y direction and this streamline, we have this theta angle. Okay, so let's calculate this body force will be equal to rho G times this dV. Okay, and so because that we are consider the force on the S direction, right? So we write this G as GS, which means that you need to do the this projection, right, on this G force, right? So make this is you have this is GS and this is some normal direction to this streamline direction. Okay, so you need to project this G vector onto this S surface and this S direction. Okay, so that's the reason why the GS, and it will showing you that I didn't draw this clearly, so let me to redraw it. So which means that if you have G here, right? So if you have this G going down here, okay, so what is this this component will be, right? You need to get this, so this will be GS, and this GS value you get it will be minus G times sin theta. You have minus sign because it's going left, okay, and times this dV. dV is the volume of this control volume, which is just equal to this A plus dA over 2 times ds. Okay, because that you have the area here, you have the area here, you average it, you get the area in the middle, and then you times this ds. Okay, get the volume. And after you do this, and remember that you have this sin theta times this ds. Okay, so what this sin theta times this ds will be? You said sin theta times ds basically is just this d. So you have this ds, right? And this is theta. So sin theta times ds, you just get this length here. So what this length it is? So this is the change of this from this point in the middle to this point. Also, what's the z direction change? So let me redraw it. Okay. So which means that this is the ds, right? So this is the ds, and you times this sin theta. You times this sin theta. So this is the thing that sin theta times ds. You just get this quantity here. So this is the change in the z direction for the center of the starting phase and end phase here. So we denote it as dz. Okay, so this will be the dz, and so this gives us the body force. Now we find both the surface force and body force. Surface force is given by this quantity, and body force is given by this quantity. And the last thing, the only thing left is this momentum flux, right? So for this momentum flux, because that we only have the momentum flux at this inlet surface and this outlet surface, so we just can quickly calculate this momentum flux. It will be this inlet surface momentum flux plus this outlet momentum flux, and for the inlet you have a negative sign because it's the inlet, because this a v dot v vector dot this a vector will give a negative value. Okay, you have this one here, and remember that we have this. You remember that for this one, okay, we can replace this one from this continuity equation because to this one. Okay, because that we know that from continuity we have this, we know that rho v times a will be equal to this one. So you can simply replace this term with this small value. This is this term. You write it inside. Okay, so this will give you this value here will give you what the net momentum flux will be for this control volume. What's the net momentum flux? So you have this one, and now you have both all this. You have this term value, you have this term value, and you have this term value. You bring this equation 2, equation 3, and this equation 4 results back to this original momentum equation. And what do you get? So you just bring it inside, and then everything else is just pure math. Okay, you just rewrite it, and so what do you get? You will get this result will be, and if you take because that this rho is constant and g is constant, density is constant and gravity constant, you can take this rho inside this differential operator. You can take this g inside the differential operator. Then everything is inside the differential operator. You can take the differential operator, to everything. So basically, this can give you that d of p of rho plus vi square over 2 plus gc equal to 0. Right, so this one can tell you why, because that this rho and this g is constant, so I can take it inside this differential operator. So when this is equal to 0, what does it mean? It simply that means that this p over rho plus this v square over 2 plus this g times z is constant. Okay, so now you see that this is the final result we get for these special cases where we make all these false assumptions, like if the problem is steady flow. Okay, no transient. If there is no viscous force, and if the flow is moving along with streamline, which means that that you do not have any flow, any flux on the bounding surface. Okay, and also we'll assume that rho is constant. You just get a very simpler form of your momentum equation. And you also can find that this equation we get here is not in the integral form, is not in the differential form. It's just a simple algebra equation. Okay, and this equation is just called the Bernoulli equation. It's a very famous equation we use in the hydraulics, okay, analysis. And so this equation, including 3 terms, right? The first term is this p over rho, right? So this is the pressure term. This is the static pressure term, right? Because this p is static pressure. And this v square over 2. This is term is the velocity square over 2, right? So this term is given by the flow motion, because this will you have velocity involved, right? So if the flow is not moving, you won't have the velocity. This term will become 0, right? So this term is going to be due to the flow motion, okay? And the last term, g times z, this is due to the gravity, right? Fluid gravity. And we know that this fluid gravity, this term, will give us the what? G will give us hydrostatic pressure, right? We know that if it's hydrostatic state, that your hydrostatic pressure will be these 2 terms should be what? Should be equal. So what, in another word, what does this mean? So if you consider for this Bernoulli equation, if we assume v equal to 0, this velocity equal to 0, so what do we get? We get p equal to minus rho gz. So this go back to our correlation we derived for the fluid statics, right? So this is our fluid static. So if v equal to 0, okay. So this is our fluid static pressure depth correlation we obtained before. Okay, so you can think that, okay, so you can think that this equation just a special case of this one, and this is working not only for the fluid with no motion. This is also working with for the fluid dynamics when fluid has motion. The only difference is that we have an additional term here, v square over 2. Right, so this is the Bernoulli equation. And through this derivation, right, you see that we derive this Bernoulli equation from the momentum equation. So you may think that, okay, so this Bernoulli equation is actually a momentum equation. That is correct. Okay, you can think in this Bernoulli equation is a momentum equation. But, okay, in another word, it can also be interpreted as an energy equation. Why? Because that if you look in each term, this v square, if you times rho on the both sides, what will you get? You get p plus rho v square over 2 plus rho gz equal to constant. So what does this mean? So this one is what? This is the kinetic energy, right? So if you times rho on the both sides for this equation. So this is kinetic energy, and this is potential energy due to the gravity. And what this one? This is this is the pressure force, which is the stress, right? And you can also consider that it's kind of energy, because that the force if you're working on a small displacement, you can change it to the work. Okay, you can think that this is the pressure work. Okay, pressure work plus kinetic energy plus potential energy equal to constant. So you can also think that this Bernoulli equation is a kind of energy equation. Okay, so what I want to explain is that although we derive this Bernoulli equation by using this momentum equation criteria, okay, because we derive this equation, all this work we done here is starting from this momentum equation. But in the end form, okay, can also be interpreted by as an energy equation. This equation can be also interpreted as an energy equation, so that you have the pressure work plus the kinetic energy plus the potential energy will be equal to constant if the flow is moving along the streamline, and also if the flow is steady, no viscous, and incompressible. Okay, so one important thing that I want to remind you, okay, is that this fall assumption we made here is very critical. Okay, so this equation, this Bernoulli equation, is only valid when this fall assumption is satisfied. Okay, so if you do not have this all these fall assumptions are satisfied, you cannot using this Bernoulli equation. Okay, and so this is the meaning of the Bernoulli equation. And as I told you before, okay, this Bernoulli equation is frequently used in the hydraulics. So what is hydraulics? Hydraulics is those that the fluid problem involving those river involving about the dam, those kind of things. Okay, and so this is a very advantage, very powerful equation. Okay, and it's a very simple form. Okay, and before we go to use the example problem to practice this equation, okay, I think I will leave it to the next class. And another thing I want to mention to you is that there is another term related to this Bernoulli equation, is so-called total pressure. Okay, if you write your Bernoulli equation in this form, right? So this P is called the static pressure. And this rho times v square over 2, right? So this is the term due to the flow motion, right? So sometimes we also give this term a name called dynamic pressure. Dynamic because they are moving, right? The flow is moving. So you can think that since this P and this one, okay, they will have the same unit, right? Because their unit has to be consistent. So you will have the P is equal to Pascal. You will see that if this term, their unit can also be converted to the Pascal. So you can also think that this is some other pressure term, and we can call it, we will call this so-called the dynamic pressure. Okay, so which means that you know, in this problem we will have two kind of pressure. The original static pressure, you know, the pressure, you know, exists when even the flow has no motion. Okay, and also an additional pressure called the dynamic pressure, which is the pressure caused by the flow motion. And so if we assume we define a new term P0 equal to P plus this rho V squared over 2, which means that if we assume the P0 will be the sum of the static pressure plus this dynamic pressure. So this will be calling the total pressure. So which means that total pressure will including both the static pressure and dynamic pressure. And if you make this assumption, so what's your final equation you got? You will get that this P0 plus rho G Z equal to 0. So this go back to the form of our static problem, right? This is static form, like, you know, that pressure depth correlation, right? So which means that now if we, you know, assume a new pressure which is called total pressure, we can convert this equation, you know, back to the original pressure depth correlation we derived for the statics problem, because that this pressure now not only including the static pressure, it also including the contribution due to the flow motion, which is this dynamic pressure. Okay, and all right, so, you know, I will just stop it here. All right, and I will stop this class here. So Friday, midterm exam. Okay, so, you know, just you know, if you have any question for the, you know, exam, please let me know. Just please, okay, please try that practice exam, so that you are going to know that because I want to make sure that you guys can really, you know, handling that has your correct setup, and, you know, to attend the exam. I do not want the cases that on the Friday, you know, you write me an email saying, oh, professor, you know, I tested on Friday, you know, this morning I found that you know, my internet connection is not fast enough to do the exam. I do not want that, okay, because that in the instruction, okay, exam instruction I uploaded on the Blackboard. You need to, if you have this kind of problem, you need to let me know at least 3 days before the exam, which means that you need to let me know before Wednesday, okay? Just try it, okay? If you have the issue, you need to let me know before the Wednesday, so that you know, I will give you another way to attend the exam, okay? And also, as I mentioned to you, that you know, the exam problem will be very close to that practice problems, okay? And all those 6 practice problems, make sure you understand it, okay? And it will be really helpful for you for the exam. And on Wednesday, try it and try to finish those problems yourself before Wednesday, because that on the Wednesday's recitation, I will let the TA to go through the answers, okay? Any question, guys? Anyone? Okay, so if there is no question, I just finish it here, okay? So, you know, just prepare well for the exam, and you know, we'll meet on the Wednesday during the exam. We'll meet on the Friday during the exam, okay? All right, bye everyone. Oh, anyone leave the message? Okay. Let's finish it.